Hey guys, welcome to the first video in probably a two-part series in which we're going to be creating an app in SwiftUI. And this app it's going to be a number recognizer. So we'll draw in numbers and it'll use a machine learning model to predict the numbers we draw in. So this model is obviously, or this application is obviously going to consist of two parts. It's going to consist of the actual application and then the machine learning model itself. And in this video, I'm actually going to be going over how to create the machine learning model. So without further ado, let's get started. So I'm over here in Google Colab, and the first thing I want to do is import TensorFlow as TF, because we're going to be using the MNIST numbered dataset to train our model. And as a result, the canvas in our SwiftUI application is actually going to conform to the same sort of format as that MNIST number model. So let's read in our X train and our Y training data, and our X test and our Y testing data. And we'll just set this equal to tf.keras datasets MNIST and load data. So once we have that loaded in, we can, here let me make sure, we can actually inspect a few properties of the X-train, such as the data type, what the actual images look like, and the shape of our training data. So you can see here, this would be one image in our data set, and it has values from 0 to 255, it looks like. Yeah, so that is what our images are. Each integer is uint8, so we're going to change that as well. And then the shape of our X-train is 60,000 or 60,000 28 by 28. So 60,000 28 by 28 pixel images. So there's a few transformations we're going to want to apply to this. The first of which is to reshape our training data so that we can use it in our neural network. So we'll use train shape of 0, so 60,000 28 by 28, and then we're adding this 1 onto the end of it. And I'm going to be honest, I'm not really sure why we need to do this. I just know that when I was trying to do this without adding this extra dimension, it was giving me an error in my model. But adding this extra 1 or dimension is equivalent to just wrapping each of these integer values in an array itself. And we'll see that in a second. Actually, let's check that out right now. Let's just print xtrain of 0. And you can see that each integer is wrapped. Okay, so that's our first transformation, and the second one we're going to do is as type float32. And we're turning these into float32 because we're about to normalize the data in a second. And we want to repeat this for our X test. So just change these. And if all goes to plan, it should work. Okay, now the next thing we need to do is actually transform our data by dividing it by 255. So as mentioned earlier, each of these values is between 0 and 255, and we want to transform them such that each value is between 0 and 1. This process is called normalizing our data. Usually we do this if we have multiple columns of data, so for instance, and they're on different scales. But in our case, we only have one really column of data, and that's the pixels. So they will all already be on the same scale. So this transformation is not really necessary. But I noticed that when I trained the model with and without the transformation of dividing by 255, when I normalized the data to a scale of 0 and 1, the model actually gave me a few percentage points higher after training. So we will do that for that reason. Okay, so the next thing we want to do is actually create our model. So we can say model equals tf.keras models.sequential And this is creating a neural network for us. And we need to add some layers, so we'll do tf.keras layers. First layer will be a convolutional layer, in which our input shape is equal to 28, 28, 1, corresponding to this up here. Our filters is 128, and our kernel size is 3 by 3. So the kernel size is the size of the window that goes across the image like this. It's basically reading out the features, and the filters is the number of feature extractions that we'll have. So we'll have 128. Okay, and I'm probably not the best at explaining this, so I'll leave a link in the description for a few articles you can go to read more in depth into kernel size and filters and convolutional stuff and stuff like that. So next we're going to add tf.keras.layers.maxPooling, so a pooling layer. And this just serves to kind of read in only the max value and eliminate some outliers. And then we'll add tf.keras.layers.flatten. So we're flattening our network. And then we're going to add our final dense layer with the units equal to 10. So it's going to give us 10 final values, or 10-dimensional vector. And we're going to say our activation function is tf.keras activations softmax. So the softmax activation function will give us these 10 values, and each value will be between 0 and 1, and they will all sum to 1. So in essence, this is like a probability distribution. And then we want to compile our model using the optimizer. We'll just say tf.keras.optimizers, and we're going to use the atom optimizer. We're going to say our loss function is tf.keras losses, and we're going to say sparse categorical cross entropy. And because we're using the softmax activation function, we need to use sparse categorical cross entropy because it's a loss function that compares two probability distributions. And the final thing we'll say is metrics equals accuracy. So if we do that, we should be good, and then we can do model.fit xtrain, fit our x training data to our y training data, and the epochs we'll set to 5. So this is going to take a little while to train, so when it's done, I'll jump right back with you guys. Okay, so now that our model has finished training, I want to do two things. I want to make a prediction function so that we can make sure our model is accurate, and I also want to save this model to my computer so that we can use it in SwiftUI. So the first thing we'll do is we'll make that function. So we'll say define make prediction, and we'll take in an image index. We'll set the image equal to xtest of image index. And then we want to do prediction equals model.predict. And we're going to pass an image.reshape 128, 28, 1. So if we don't add this extra 1 right here, our model is going to throw an error, and that's why we're doing the reshape. And then also we'll do plot.imShow image.reshape 28 by 28. We don't need this extra 1 right here. And then we can just do print prediction.argmax like so. So prediction is actually going to give us a 10-dimensional vector in which each value is the probability that it's the given number. So we need to take the value with the highest probability, and that's why we're doing .argmax. Okay, and then let me also import matplotlib.plyplot as plt. And now this function should be good. We'll just do make prediction of 0. And you can see our model predicts 7, and the image is showing 7. So if we try this again, 6, the image is showing 6. 1,000, just the image index. Perfect. So we know that our model is accurately classifying images. So the last thing we have to do is we have to save this model to our computer. And to do this, we can just do model.save. We need to specify a path. So we'll just say content model, and then we want to do zip content, this will be our name, download model, recursive, and then we'll just do content / model. So if we do this, we should get the download model.zip, and you will see model actually show up. I already had it saved there. But once we have that, we can just do download. And then if we jump over into the terminal, I'm going to cd into my ML folder. It doesn't really matter where you go, and move over from downloads the download model.zip. Okay, move it to where I am right now, and then I can do unzip download model.zip. Okay, you can see I have this new folder named content. If I cd into content, it's going to have my model. So I'm going to move my model. Back one, or I guess let's just move model to ML, and we can remove content, or remove rf content, and the zip file. We don't need those anymore. Now we have our model, and this is actually a TensorFlow model, so we're going to need to convert it to a CoreML model, and to do that we can just do convert.py, import TensorFlow as TF, so we can load our model, import CoreML tools as CT. We want to do model equals tf.keras .models load model, and we'll just pass in model, which is the file name of our current model in our directory, and we can do ml model equals tf or ct.convert model, and then ml model.save. We'll just name this image. We'll do MNIST image recognizer, like so. And when I do Python 3 convert.py, if I coded this correctly, it should work for us. It's going to take a few seconds though, because these libraries are kind of cumbersome. Alright, looks like it successfully executed, and we have our MNIST image recognizer.ml model. So that's all I have for today's video. We're going to use this MNIST image recognizer in our SwiftUI application so that we can predict images. So I hope you guys enjoyed. I'll see you guys in the next one.